Hello there. We are very happy to have you all here. To begin the seminar, I'd like to introduce you to the Director of UCAR's Scientific Partnership and Services Center, as well as CPAESS, Hannah Moriello.
Thank you, Dawn, and welcome everyone. We are delighted to have you attend the CPAESS Discovery Seminar Series. CPAESS scientists do everything from explore our ocean depths, to fly into hurricanes, to take critical measurements, to heliophysicists modeling coronal mass ejections, to those who unravel the mysteries of the Arctic. And we want to share this with the public, the NCAR, UCAR community, and our many colleagues at universities across the globe. Just to orient you all, we are using Slido located below the presentation screen so that you can pose questions for our speaker at any time during the seminar, and they will be answered after the presentation. It is now my sincere pleasure to introduce to you today's speaker, Dr. Marcela Ulate, who is a UCAR.CPAESS project scientist at the U.S. Naval Research Laboratory, NRL, in Monterey, California. She researches seasonal to subseasonal ensemble forecast validation using the Navy's Earth System Prediction capability, Navy ESPC. Marcela also works as a lead developer for transitions for the coupled ocean atmosphere mesoscale prediction system, COAMPS, directed energy and optical turbulence applications. Today, Dr. Ulate will be speaking on the impact of Stochastic Kinetic Energy Backscatter scheme on the Navy Earth System Prediction capability, Navy ESPC, in predicting the Madden-Julian Oscillation during 2017. Please join me in welcoming Marcela.
And yes, I would like to acknowledge my collaborators, Caroline Reynolds, Will Crawford, Mike Janica, and Justin McClay, who also work in NRL Monterey, who help a lot with this work. So talking about different timescales in predicting for the Navy, we have different components. We have the hourly today's forecast, which is what the Navy uses usually for fleet safety and operational readiness. And in this case, the Navy uses COAMs or the mesoscale and also the global weather and ocean models. In the timescales or of weeks and months, usually the Navy needs this type of forecast for ship routing, force positioning, operational preparedness, and situational awareness. And these type of forecasts are in the timescales of the week to months. And the Navy capability that we had available for this is the Navy Earth System and Prediction Capability, or Navy ESPC, which is a new capability, and it has new products. It's a couple model that uses NAVGEM as atmospheric model, HICOM as ocean model, CICE as ice model, and it has a wave model also called WaveWatch 3. Another timescale that the Navy is interested is the seasonal timescale, or far away from the seasons, which they usually use climatology or historic analogs, for example, to forecast ENSO. And this is done to plan in the long range planning for training exercises and for intelligence. A little bit more about the Navy ESPC system. It's a global model, about 37 kilometers with 60 vertical levels. It uses the Earth System Framework, Modeling Framework, ESMF, and the National Unified Operational Prediction Capability, or NUOPC layer. It uses ocean model, which is HICOM. HICOM has a resolution in the Navy ESPC system of 1/12 of a degree, and it has 41 vertical levels. It also uses the community model ICE code, or CICE, with a very high resolution also of 1/12 of a degree. And I'm going to talk about here about the ensemble capability. And in this case, we have two. We have the regular ensemble, which uses data assimilation perturb observations to create its ensembles. It has 7 members, and it's run up to a 45-day simulations length weekly. So, and operationally, it has 16 members, and it's also run weekly. So this is just a little scheme of the Navy ESPC system and the different components. As I mentioned before, it's a fully coupled model on the ocean, and it has a nice model as well. So more specifically, I'm going to talk about the Stochastic Kinetic Energy Backscatter ensemble or scheme used for Navy ESPC. So Stochastic Kinetic Energy Backscatter is usually just called a SKEB. And this scheme is used to stimulate or simulate upscale propagation of errors caused by unresolved grid scale processes. So you're trying to perturb the ensemble so you get some of that variability that in the subscale. And the implementation in NavGen, which is the atmospheric model that is used in Navy ESPC, it's used by using a moisture convergence to determine the vorticity perturbations location. So basically, whenever convection is happening, then that's where the ensemble perturbs, and then it uses this moisture convergence mask updated every 2 hours in order to perturb the ensembles. So it was designed so you account for all that variability that happened in the subgrid scale when you get moisture convergence. This ensemble has 5 ensemble members, and the forecast is run at 30 days. Remember that the operational is run at 45 days, so this is a little bit shorter. And something important to notice is that the SKEB forecast and the control or the regular ensemble forecast use the same initial state as the control. So basically the main objective of SKEB is to correct the energy spectrum by accounting for all those unresolved processes that happen in the processes that are not resolved directly by the model scales. So a little bit about the Madden-Julian Oscillation and why this fits in this work. This is the one of the many plots that you can show for Madden-Julian Oscillation, or MJO, which is the leading mode of intraseasonal variability. It's an eastward moving intraseasonal disturbance. In this plot to the left, you have time going down, and these are the different phases of the NJO, starting from phase 1 to phase 8. These are precipitation components. So in this case, you can see how the different the bulbs of precipitation just move eastward, starting from the Indian Ocean all the way to the maritime continent. And this disturbance will travel around the world, and it's linked to winds, westerly winds in the surface and easterly winds aloft, associated with each one of the different phases. And it has a period between 30 and 60 days. And the MJO, it's that intraseasonal link, but it's also very important to forecast because it has a lot of teleconnections of all different timescales. For example, it has there being a lot of research about MJO and the modulation of the monsoon onset. It also modulates the tropical cyclone frequency, depending on the large-scale patterns and the wind shear during MJO events. It is also linked to rain events on the west coast of the United States, and also longer timescale phenomenon as ENSO, where the NJO is linked to ENSO's periodicity, the timing, and its predictability. So NJO is a good measure whenever you want to account for a model to see if that's a good forecast, because it's linked to short time scales and longer time scales. So the goal of this research is to examine the impact of SKEB on Navy ESPC performance. Specifically, we focus on tropical precipitation, and we measure this by using the precipitation, but also the outgoing long-wave radiation, or OLR. We're going to look a little bit at the sea surface temperature and, of course, the MJO. We also are going to show some results of the spectral analysis of different ensemble metrics in order to study if these different errors and how these errors evolve and spread between the SKEB and the control simulations and how they differ. So the methodology that I'm gonna use, first we have the control ensemble, which is the regular Navy ESPC ensemble, which is run once a week. I'm using the 2017 and 1 month in 2018. So overall is 53 different ensemble runs. The SKEB runs are the same time period, the same frequency, but the length is just 30 days. So we're grabbing the first 30 days of the control ensemble simulations. We are using daily means from 3-hour and for 12-hour outputs. And remember that the resolution of SKEB is 37 kilometers, but we're going to downgrade to 1 degree resolution, mainly because of verification purposes. And for this verification, we use NOAA OLR from the climate data record, and the resolution is 2.5 degrees. We also use SSTs from NOAA Optimum Interpolation SSTs, which version 2.1, and that resolution is 2.5 degrees. And to validate or do verification of the precipitation, we're going to use iMerge, which is integrated multi-scale multi-satellite retrievals from GPM. And for other different fields like geopotential height or winds, we are going to use ECMWF version 5 reanalysis or ERA 5. And their native resolution is around 31 kilometers, but we're going to downgrade to 1 degree. And among the metrics that we're going to look at are the ensemble spread, the root mean square error, and bias of the ensembles. So these are some plots of the general ensemble statistics for Navy ESPC. So throughout my presentation, I'm going to color code the SKEB simulations on red and the control simulations on blue. And these are plots of ensemble variance, and these are global plots. So the mean ensemble variance globally. In the top, we have geopotential height, and then in the bottom left, temperature, winds in the right, and in the winds at 250 in the right, and in the bottom, we have winds at 10 meters. And in the y-axis is the variability, the variance of this ensemble. So you can see first that the greater variance are in the SKEB runs. And you can see this by looking that all these red plots are basically on top of the blue plots, which means that the SKEB ensemble do get more an increase in the variance globally for all these variables, for geopotential height, winds, and 2-meter temperature. The Navy ESPC is an under-dispersive model, but by using a SKEB, you improve a little bit this ensemble system by increasing the spread. And the results are consistent with different levels. Here I'm just plotting at 500 and 250, but you get the same results at different heights. And you can also see from this plot of the wind close to the surface that after day 15, it kind of the curves kind of flatten out, and they start saturate. And this usually happens around day 20. And it's very clear seeing in the wind, but you can also see it a little bit in the wind at 250 and in geopotential height. So overall, this is good. because this is showing that SKEB increases the ensemble spread for different global metrics. This plot in this slide is very similar to the one I showed before, but in this case, I am showing the different ensemble statistics, but for the tropics. So the previous one was global, and this one is tropics. And we expect SKEB to have a larger impact in the tropics because it was designed to perturb, to the ensembles to be perturbed whenever convergence is happening. And we know in the tropics, we get a lot of convection. So you get greater impact. You get a lot of impact in the tropics. So I'm showing the same variables from the previous plot: geopotential height, winds at 250, 10 meters, and then 2 meter temperature. And these are tropical means. And you can see again that the red line is above for most of the time. Around day 20, you see that the ensemble starts to saturate, so the lines kind of flattens out, and so you get similar and or enhanced impacts over the tropics if you compare with the previous ones that are globally, which is also good news. Adding different variables here. In this case, I am showing here outgoing long wave radiation, sea surface temperature, and precipitation. And you can see from these plots, and at the top, we have a spread, in the middle, bias, and in the bottom, root mean square error. And this is all statistics calculated with the full data set. These are tropical means. Again, you see and these are usually variables that are not common to use in the ensemble statistics, but since we are gonna look at the MJO, and since the SKEB works mainly whenever there is convection, I think looking at these variables is important and adds value. So we see again that the red line is above the blue line for most of the different variables and the different metrics. You can see it in the spread in the top left for OLR, SST, and precipitation. The precipitation field is a little bit noisy, but that's why we also plotted outgoing long wave radiation, because it's usually smoother and a proxy for precipitation. The reason why you see the red line in, below the blue line in the OLR case for the bias is because the OLR values are opposite to the precipitation. So usually precipitation is associated with negative OLR values. So that's why the line is below the blue line. But basically it means that you increase the spread, reduce the bias, and reduce the error. And this is true for OLR, SST, and precipitation. And something important that this SST's ensemble metrics show is that the perturbations are done to the atmosphere, but somehow they propagate to the ocean as well via coupling, and this will contribute to the improvement of the errors and reducing the bias and the spread also in the ocean, which is also a good result, and it's not a trivial result. And this is done through the coupling. In this case, I am showing plots of the different ensemble metrics that I've been showing. We've divided here by different lead times. In the top, I'm showing day 1 to 5. The middle is day 13 to 17, and in the bottom is day 26 to 30. Just to see how these different errors and how the spread evolved throughout the simulation period, and which locations were having the greatest errors and the largest spreads. So in the left, we have the errors, the root mean square error, and in the right, we have the spread. And the color bar is the same for both. So basically, first you see that the errors, the location of the errors and the spread is the same, but you can see that the error values are greater than the spreads. This is all through all the lead times. You can see it by just looking at the different colors. The largest ensemble spread for sea surface temperature is concentrated in the western boundary currents. So it's these darker colors that you see over here, which also are linked to high error areas. So you get large spread in the western boundary currents in the north and south hemisphere. Also, the regions with large errors generally have large spread. And overall, the sea surface temperature spread is too low compared with the errors. And we may need some stochastic forcing in the ocean. But you can see that these errors occur in the same location throughout the simulation. It's not that they come and go in different locations. It's mostly the western boundary current, Southern Ocean, Equatorial Pacific. And this is consistent with all during all lead times. If we're looking at the sea surface temperature error and bias here, we just wanted to quantify where are these largest errors and if they are positive or negative. So that's why we're looking at the bias here. In the right side, again, we're plotting for SSTs for the first 5 days, the middle 5 days, and the last 5 days of the simulation. So the first thing is that we see a warm bias in the Eastern Equatorial Pacific. So it's all these warm values over here, and this is very prominent around the middle of the simulation. And you also see a warm bias in the Southern Ocean throughout the simulation, the first 5 days, the middle 5 days, and the last 5 days. We get a cool bias in the West Pacific, which is very clear in this region, and it seems to be there all the time. And these biases seem to increase with lead time as well. If you look at the different colors, you can see that they get darker as you go forward in the lead time. If you compare the first 5 days with the last 5 days. So overall, the Navy SPC ocean is too warm, and the control and the SKEB simulations show the location of the biases. The biases location are in the same areas. I'm showing a SKEB in here, but the location of the bias is the same as in the control. What it changes is just the magnitude that in the SKEB, but the bias are smaller. Moving through outgoing long-wave radiation biases for the control in the left and for a SKEB in the right for the first 5, the middle 5, and the last 5 days of the 30 days. So negative means convection is too strong, right? The blue values, and red is convection is too weak. So mainly we get weak or almost weak convection everywhere, especially in South America and in the Atlantic and the East Pacific. The SKEB and the control have the same problematic areas. You see convection is too strong over South America, maritime continent. You can see the areas are basically the same between the control and the SKEB. What it changes a little bit is the actual magnitude of these biases. Again, the convection is too strong over the Central Indian Ocean and maritime continent, and a little bit in the West Pacific and over South America. And these biases increase with lead time. So despite the fact that we get good ensemble statistics, we still see that the convection is a challenge to forecast. And we measure this by the OLR. If we look at the differences between SKEB minus control for OLR, so we wanted to see if these biases actually will increase or decrease, and where, in which areas, if we're looking at outgoing long-wave radiation. So in the left, we have the bias differences, SKEB minus control. In the right, we have the root mean square error difference, SKEB minus control as well. And then, so we see that in general, the SKEB reduces the bias. So you see a lot of blues, which means that the SKEB is reducing the bias, mainly in the tropics. We get the larger corrections occur in the longer lead times. At the middle of lead times, as you can see in the middle panel here. However, at the end, at the last lead times, it just gets very noisy, and the SKEB is better at correcting the biases in regions where the convection is too weak. If you compare with the plots that I showed before, and sometimes it amplifies the biases in regions where the convection is too strong, like in this case, we're seeing in the Maritime continent and the West Pacific. And as the spatial pattern becomes very noisy after day 20. So basically, the SKEB improves in most regions where the convection is too weak, and the impact on the West Pacific is mixed because we see that the difference there are large. So overall, if we plot spread in the y-axis and root mean square error in the x-axis for the tropics, for outgoing long-wave radiation, this is a measure of your ensemble, and the lead time are the different colors. This curve is for the control SKEB, for the control ensemble, and I'm plotting here in the circles the SKEB root mean square error versus the spread. You see that there's a gain on spread when the SKEB is used, and there is a reduction of the error, which is what we want to see. And we see this as well in the sea surface temperature. Here, the two curves, the triangles are for control, the circles are for SKEB, and the different colors are different lead times. So we get corrections made by SKEB. They are indeed making the ensembles less underdispersive, so it's correcting the ensemble in the right way. And that means that we are decreasing the error, but also we are increasing the spread. And while there are no direct perturbations done to the ocean, the atmospheric perturbations are able to improve also, are able to be a coupling to improve the ocean, which is reflected in this sea surface temperature plots. So this is good news. And going back to the Madden-Julian Oscillation, and in this case, I am showing 3 different cases of 3 different scenarios that we have with Navy ESPC and on forecasting the Madden-Julian Oscillation for 2017. We have an MJO event. So in this case, we're using the ROMI index, which is based on the outgoing long-wave radiation. So it's smoother than other indices there. And basically, in this plot, the different numbers show the different phases of the MJO and location. And as it's saying in each side of this plot, the black lines are observations. Again, the blues are control, and the reds are SKEB. And you can see this is the case where there is an MJO event. And you can see that in this case, the event was forecasted by the Navy ESPC, by both the control and the SKEB simulation. The SKEB curves for the ROMI index for this MJO case seems to be closer to the observation. So this is this black line and the red line here. Control seems to be a little bit stronger. So it seems that for this case, the use of SKEB, it is actually correcting a little bit the MJO forecast. And the observations within the SKEB ensemble, you see that there is just a larger spread. These are the different members of the light blue, the light pink colors and the light blue colors. If we look at another case where there was no MJO at all in the observations, you can see that there is also no MJO in the model, which is good. But the magnitude of this index also changes a lot. In this case, we can see that, again, if you look in detail, the bright red line and the black line, you can see that they're closer together. So the SKEB forecast is closer to the observations. And you can see also that all the blue lines will kind of are outside of these circles, which means that it is slightly strong than the observations, which is also which is not showing similar stuff as the observations. And another case is a false MJO forecast. So this is in the right side. So we have no MJO event. These are the black line here is inside the circle. And then the Navy ESPC control and the SKEB both are showing a very strong MJO forecast. So in this case, both simulations are forecasting an MJO that is not in the observations. And you can see that this is true for both the control and the SKEB. However, if you see the bright red line is closer, it's inside of going back to the small circle. So it is trying to correct, but it doesn't really correct the forecast. So there was a fictional MJO in the model, in the control run, and the SKEB simulation, it's just basically running showing the same. So now I'm going to switch gears a little bit, and I'm going to show some results of spectral analysis that we have done for this different ensemble statistics. And we decided to do this spectral analysis because we wanted to see how these biases and errors will change or will vary depending on the scales that we're working with. So what we did was calculate a one-dimensional spectrum in the x direction. And we calculate the spectrum for the root mean square error, the ensemble mean error, and the ensemble spread. And then we do an averaging over different areas of interest. We do the globe, we do the tropics from 10 to 10. We do the south and the north hemisphere from 35 to 50 south and 35 to 50 north. So these are these three areas, the tropics, North Hemisphere and South Hemisphere, and then we do the globe. And for this spectral analysis, we are using seasonal averages. So all those 53 different runs, we move them, we select by time of the year, so we get the 4 seasons. And in this slide here, I'm showing the spectrum of the ensemble perturbation. So this is, we're plotting here ensemble minus ensemble mean. In the top, we have control, and in the bottom is a SKEB. I'm showing December, January, February with, and these are 10-meter winds, and the location for this is the tropics. So in the y-axis is the kinetic energy of the energetics of the spectrum. And in the x-axis, we have the planetary wave number with the smaller values in this side. And the different colors are the different lead times. So shorter lead times are the warmer colors, and then the longer lead times are the cool colors. So as I mentioned at the very beginning of this seminar, both the control and the SKEB have the same initial analysis. So at lead time 0, they are the same because, and so this darker red line is the same for the control and the SKEB, and we can use it as a measure and see how they change. So for example, you can see that in the case of the control, you get all these different ensemble spread closer together for the different lead times. And then in the case of the SKEB, you get that these different lines, there is a big jump from lead time 0 to 1 to 2 that you don't get it in the control. And also, you do see that when you're plotting for the different planetary wave numbers, that they are below this tau 0 spread, which means that there is loss of a spread right after the ensemble starts, and this happened for large wave numbers. And if you see this plot for the SKEB, you do see that loss, this jump from the dark red one to the different colors, it does happen, but it happens in is less drastically, and which means that the SKEB is able to retain most of the variability at small scales that are lost by the control. Also, in this plot, I'm showing just selected lead times, day 5, 10, 20, 30 for the control in the blues and the SKEB in the reds. And the purple line here is the same as this tau 0 line. And basically what we're looking at is this jump from the purple to the blue in the control, and then to the red in the SKEB, which is the gain of spread that you're starting to get even after day 1 in the SKEB simulation. And then you get it throughout the different lead times, and by lead time 20, 25, and 30 is starting to saturate. And as I was mentioned before, you also get this jump here from the blues to the red, and you're able to retain more of that spread that you're first losing, that you don't get in the control simulation. You're able to gain it back with SKEB, which is also good. And by day 2, you can see that it just had gain. It just went back to the large scale. So this is that jump that I was talking about. In this case, I'm showing day 5, which means that whatever we're perturbing the subgrid scale, but by day 2, it's already reached the larger scales. So it happens fast, and which is ultimately what we want. In this case, I'm showing the same. I'm showing ensemble perturbations or the spread. And this is the different seasons for 10-meter winds, and all this is over the tropics. But we get similar results, the same results in different areas as well. So in the top, we have DJF. In the bottom, we have June, July, August, and then March, April, May, and the top, and in the bottom, September, October, November. And you see that this increase in the spread in the first 1 to 5 days, that jump in the spread in the low planetary wave numbers from the control to the SKEB happened in all the different seasons. In all the different seasons, it's also consistent that you're able to retain more of the spread that is lost with control, which is also good. And in the right hand side here, I am plotting just June, July, and August for 3 different areas. So this is the North Hemisphere, South Hemisphere, and then global means. And you can see that you get different, the same results in the same, even though the area is different. You get that the results are the same in the different areas for the different seasons. However, the gain in the spread is most evident in the tropics, where the energy spectra is lower to begin with overall, because we don't get the higher baroclinicity events that we get in the North and the South Hemisphere. So even though the spectrum values are smaller, you still see great changes. but these are all consistent among the different areas. In this case, I am showing winds at 850 hectopascals. Before I was showing at 10 meters. This is also just for the tropics. And we see we have a control at the top, SKEB in the bottom, the same type of plot, and you see that that you get a lot of, in this case, you don't get that loss of spread at the beginning, that as it is very clear for the winds at 10 meters. In the case of the SKEB, you see that you're even able to start by day one even a little bit higher than that tau zero line in the control, which is also good. And you also see that there is this big jump from the tau zero spectral line to tau to lead time 1. There's already a gain on the spread that it has reached already low planetary wave numbers because of all the SKEB perturbations. And we see this little bump here that I'm probably going to get a question. We still don't know why is this bump present. We're looking into it to try to see what it is. It doesn't show in the 10-meter winds. It shows in the winds at 850 and 200. So we're trying to figure out why there's this little increase in the spectral energy here at these larger planetary wave numbers. So we're still trying to look into that, and we're trying to do some plots, but we may think that it could be artificial. And it's also important to consider that all the results that I'm showing here, these are just one-dimensional spectrum, and there have been papers previously published that suggest that it is better to do a two-dimensional spectrum. So we're planning to do this in the two-dimensional spectrum in the future. So maybe this bump will disappear, but we're going to look into that. Also, we get very similar results for the wind at 200 hectopascals. As I was saying, this is showing here on the right. Again, you get that just jump in the curve from the purple all the way to the red that is higher from the control. And this is for DJF and the tropics at 200 hectopascals. So you see it is very consistent among the different levels. In this case, these curves are for 200 hectopascal winds, and you still see very similar. Then you see it close to 850. You see that the SKEB is able to gain that variability, even gain a little bit more. I'm just going to go back so you see it at the very beginning. This is close to 10-meter wind, so you get a loss at the beginning that you're not able to get it back from the SKEB. You gain it a little bit, but if we look at the 200 winds and 850 winds, you do see that all the lines are basically above that first tau zero line. And I'm just going almost to the end here. These are ensemble mean errors. So before I was showing the ensemble spread, this is a measure of the errors here. So this is the spectrum on the ensemble mean errors. This is again for December, January, February, and 10-meter winds for the tropics. Planetary wave number is in the x-axis, and this purple line is a tau zero, or at the beginning. It is very difficult to see the distribution of the light here, but you can see it from this plot here in the bottom, which we are doing control minus a SKEB. And I'm just choosing different lead times here: day 5, day 10, day 15, day 20, day 25. So you see that shorter lead times have similar errors between control and SKEB, but closer to the surface, the error corrections seem to occur at larger scales. So there's a lot of corrections happening here. And in this, and also smaller in the smaller wave numbers, because we see that the changes here are small. However, the energetics are small in here. So, the values of this curve are smaller. But overall, we see that the difference in the ensemble mean errors show that the errors are greater overall for control. So this is basically, these different lines here are greater than 0 for most of the time, which means that, yes, the error is greater for the SKEB, especially, and it is hard to see, but yeah, it is larger in the control mainly for basically all different planetary wave numbers. So going back to the MJO and that plot that I showed before, then where I'm showing here some of these different ensemble spreads and ensemble spreads and ensemble mean error spectral. And I'm just going to go back. Remember, just the first event is an MJO event. The second plot is a no MJO event, and the second one is a false positive. The third one is a false positive. And if we look at the ensemble spread at the top and the ensemble mean ensemble mean error at the bottom, we can from those specific cases, and then if we look at the ensemble mean error for those cases, here the different lines, the bright blue and the bright red are day 5, and the light blue and the light pink are at day 20. So we can see for the no MJO event that the smaller spread occurs at large wave numbers versus the no MJO event. So you see that you get that the value of the area that these lines cover is larger if you compare whenever there is no MJO event, even the no MJO event and the false positive, which is no MJO event as well. You see that the larger errors overall occur in the for the MJO event. The control errors are larger overall through the simulation. This is for the NJO event. In the case of the no NJO event, you get a larger spread, larger wave numbers. So basically, if you compare this event, these two plots in here, and this one compared to the MJO event, you get larger spread overall for both cases. And you get larger errors for SKEB at lead times between 5 and 15, 5 and 20 days. And you get similar results for the no MJO or the false positive event. So in conclusion, my conclusions are that the SKEB ensemble perturbations have a beneficial impact on the ensemble performance. So this is shown by, in general, increased spread, lower errors, and lower biases. The Navy ESPC underproduces convection and precipitation in the tropics, with the exception of the maritime continent and the West Pacific, where it's convectively overactive. Also, the atmospheric perturbations improve ocean forecasts via coupling through, however, the ocean is still under dispersive. The Navy ESPC is a skillful tool to predict the MJO. SKEB shows some improvement on a case-to-case basis, but not systematically. And it is hard to make a specific conclusions about the MJO, since it's just 1 year of data and they're just different cases, and it just basically depends a lot with each case. And also the SKEB seems to be increasing the spread in the smaller scales closer to the surface, with the little change in the errors for such scales, and most of the error improvements occur in the larger scales. And future work, we're going to try to use a larger data set just to quantify the MJO performance overall. We want to do more in-depth analysis on the MJO forecasts, mainly case-to-case basis, just to better understand the sources of error for each case. And we also are planning on do some analysis, trying to analyze the sensitivity to the ocean, to oceanic atmospheric model resolution. I don't know if you remember in my very first slide, the ocean resolution here is 1/12 of a degree, which is very high resolution. So we also want to try to account for sensitivities to ocean resolution. And that's it. Thank you, and I'm open for questions now.
Thank you so much for sharing your great work with us, Marcela. We truly appreciate it. And now to our Q&A portion of today's seminar. I'd like to direct everyone's attention to the QR code on your screen. And please enter your question here for Marcela. And while you're doing that, I would like to invite you all to attend our next seminar on Wednesday, July 19th. At 11 a.m. and that's Mountain Time, with Dr. Wenhao Dong, CPAESS project scientist at NOAA Geophysical Fluid Dynamics Laboratory, DFDL, who will be speaking on simulation mesoscale convective systems using DFDL's new high-resolution general circulation model.
It looks like we have a question from, and I hope I'm pronouncing your name properly, Jimmy Dudia. Hi, Marcela, interesting talk. The SST and the preset biases were reduced with SKEB. Any idea how the SST bias was improved? And was a preset bias improved in the same areas? Thank you for your question, Jimmy.
Yes. I didn't look in detail to see if the exact same areas are the same for the SST and the SKEB, but probably they are, just because the SKEB is set up to perturb whenever convection is happening. So my guess was probably yes, but I can look into that more. Thank you, Jamie.
If anybody has any questions, please post them now. As someone who is not a scientist, I would just say, could you go over, you had mentioned some of the things that you would like to do to improve predictive skill of this model. Could you touch on that a little bit more? Thank you, Marcela.
In the future work?
Yes.
Yes. So, you know, getting just 1 year of data for the MJO is quite restrictive, and it's usually very hard to do generalizations on how it is the MJO performance when you have a lot of cases. So we're trying to figure out what is a better way to look at it, if just case to case, or just try to combine everything and you know, do by different classifications of that ROMI index and by MJO phase. And also, since the ocean resolution is so high for Navy ESPC, we want to try to test how this resolution will impact the forecast of the MJO as well. So this is all future work, as well as redo this by using the two-dimensional spectrum, which I think will probably get more information on how these different errors will propagate. And if you have any comments, you can also email me, because or if you have any ideas, you can just email me.
I would like to thank all of you for coming to this UCAR.CPAESS Discovery Seminar. And I also just want to remind you to go to our website to find out of our future talks. The website address is cpaess.ucar.edu. And here you will find, or you'll be able to find a link to this talk after it's uploaded to YouTube. Marcela, our sincere thanks to you for sharing your important research with us today. I also want to thank Jesse of UCAR Multimedia Services for his invaluable assistance. I hope to see all of you for our next CPAESS Discovery Seminar on Wednesday, July 19th, 2023. And good afternoon, everyone. And again, thank you for joining our CPAESS Discovery Seminar today. Thank you.
Thank you.